Swayam Prabha. Digital India. Educated India.
So our next speaker is Koya Nakashima, and the topic of the presentation is development of scheduling system for batch processes considering heat recovery with heat storage tanks. So Koya, over to you.
Yes. Can you hear me?
Yes, I can see your presentation. You are audible. Please go ahead.
Okay. Good afternoon. My name is Koya Nakashima. Now, I'd like to start presentation with a title like this. When energy conservation is worldwide. Energy consumption in the industrial sector accounts for about 46% of the total, of which about 18% is accounted for by the chemical industry. Chemical plants, which consume a large amount of energy in the chemical industry, are broadly classified into continuous processes and batch processes. Unlike continuous processes, batch processes mainly produce high value-added products, such as pharmaceuticals and fine chemicals. For batch processes, there has been a lot of research on scheduling, considering cost and resource allocation. But energy efficiency has not been a major consideration due to the high added value of the product. However, energy conservation is now required in batch processes. Here, I will briefly explain the difference between heat recovery in a continuous process and batch process. In a continuous process, as shown in the figure on the left, hot stream and cold stream are always present, so heat recovery is possible as long as the temperature conditions are satisfied. However, in a batch process, hot stream and cold stream do not always exist at the same time. Thus, making heat recovery design is more difficult than in a continuous process. In recent years, to compensate for this disadvantage, the number of studies incorporating indirect heat recovery, which uses a heat storage tank for heat recovery, has increased. However, previous studies have not examined the details of heat storage tank, and it was unclear whether the heat storage tank would be effective in terms of cost. Therefore, the purpose of this study is to develop a scheduling system that considers heat recovery for batch processes, and to examine the effectiveness of indirect heat recovery using heat storage. From this section, I will explain two topics. First, I will explain the scheduling system for batch processes that considers heat recovery. In this study, we assume the process that produces two products from three raw materials, which is a very common process in the study of batch process scheduling. This table shows the data required for heat integration. This process first performs reaction 1 using feed 2 and feed 3 to product intermediate 1. Next, feed 1 is heated by a heater to produce hot 1. Then, reaction 2 uses this hot 1 and intermediate 1 to produce intermediate 2 and product 1. Next, intermediate 2 reacts with feed 3 to product intermediate 3. Finally, intermediate 3 is separated to product 2 and intermediate 2. This intermediate 2 is recycled. The above is general flow of the target process. Next, I will briefly describe the overall system constructed in the study. A genetic algorithm is used for scheduling, and each individual represents a schedule. The production volume is then determined based on the schedule of each individual. Next, if heat recovery is feasible, a heat recovery design is performed. During the heat recovery design, if indirect heat recovery is possible, a heat storage simulation is performed. After this heat recovery design, the cost of utility for running the schedule is determined. These are performed on all individuals of generation N, and all individuals are evaluated in terms of product volume and utility cost. The next generation is then created by genetic operations such as selection, crossover, and mutation. In this study, we use two chromosomes to represent a single individual based on the method of Mashi and others. The first is a time chromosome, which represents the duration of the time period when the schedule is divided at the number of event points. The second is the instruction chromosome, which represents the operating conditions of each unit at each time period. Now, I will explain a specific example, assuming that the time horizon is 12 hours and the number of event points is 6. First, time horizon 12 hours are divided into 6 points according to the time chromosome. Since the target process has 4 units, operational conditions at each time period can be represented by 4 genes. For example, the first time period looks like this. Heater executes the job represented by 1, and reactor 2 executes the job represented by 1. Also, since still is 0, nothing is executed. Finally, a schedule can be converted by setting the operating conditions of each unit from the instruction chromosome for all time periods. Now, I will explain the evaluation methods. As a fitness for GA, we use a combination of 2 indicators, the normalized value of production and utility cost. The formula is shown here. The W in the formula is the weight of how much importance is given to the normalized product volume, which is set at 0.75 in this case. The initial cost of heat storage tank was estimated as a shell and tube heat exchanger, and the annual cost of utility was calculated, assuming 340 operations per year. In calculating the cost of utility, we use the unit cost of utilities shown in this table. The above system was used to compare with the scheduling and heat recovery design results from other methods. We assume the 2 patterns of time horizon, 12 and 20 hours, for the process that produces 2 products from 3 raw materials previously described. For the scheduling, we also assume that there were no restrictions on the amount of supplied feedstock or stored product. On the other hand, intermediates could be temporarily stored in a storage tank, and the capacity limit was set. These are all similar to those used in the comparative literature. The parameters of GA and termination conditions for the simulation are shown here. The table below shows the most highly evaluated individuals obtained at the end of the simulation and the results obtained by the other methods. Middle 3 columns show the production volume, and the right column shows the total utility usage. The area painted in red is the result of this study. Regardless of the time horizon, it can be seen that our method obtains reasonable results in terms of both production volume and total utility usage, comparing with other methods. These are the results of the scheduling system and comparison with other methods. From this section, I will examine the effectiveness of indirect heat recovery using heat storage. First, I will explain the heat recovery design method used in this study. A shell and tube type tank using phase change materials was used to study the heat storage system. For the heat storage system, we assume that all tubes behave uniformly and considered heat losses from the shell to the surroundings, axial and radial thermal conductivity of the PCM, and local film temperature difference between the heat transfer fluid and the PCM. Since PCM involves a phase transition, the phase transition of the material must be considered when performing the simulation. Such a problem is known as the Stefan problem, and in this case, we use the enthalpy method, which is often used as a solution method. In the enthalpy method, enthalpy conservation equation shown here is applied to a volume element and takes finite differences of the equation. Then, the enthalpy is obtained by finding the solution using the Gauss-Seidel iteration method. To examine the effectiveness of a heat storage tank, we use a heat storage simulation system to study the effect of the amount of PCM on the same schedule. The PCM amount is set to 4 conditions shown in the upper table, and the tank conditions are set as shown in the lower left table. In this simulation, we choose a PCM that occurs a phase change in the intermediate temperature range, since the temperature range of the target process is 50 to 130 Celsius. Here are the 2 schedules we use for the comparison. Heat recovery design was performed for Schedule 1 and 2, shown in these 2 Gantt charts. Schedule 1 is the one with the highest evaluation among the individuals obtained in the simulation, and Schedule 2 is the one with the higher heat recovery by the heat storage tank. This figure shows the heat recovery rate for each PCM amount on the left, and the annual cost of utility for each PCM amount on the right. Schedule 1 is indicated by the blue line, and Schedule 2 by the red line. Schedule 1 shows good heat recovery rate and annual cost of utility in proportion to the amount of PCM, while Schedule 2 shows the best results when the amount of PCM is 50 kilograms. This means that, depending on the obtained schedule, there may be an optimal value for the amount of PCM. Given the above data, I will now consider why tank A has a higher cost of utility than tank B in Schedule 2. First, let me explain the heat transfer between the heat storage tank and process stream. As shown in the figure upper right, PCM in the heat storage tank and process stream transfer heat by a heat transfer fluid. Therefore, in general, as PCM amount in the tank increases, the amount of energy exchanged between the heat transfer fluid and the PCM increases. In this case, since tank A contains more PCM than tank B, the temperature difference of heat transfer fluid between the inlet and outlet of the tank is expected to be larger in tank A. This figure shows the outlet temperature of heat transfer fluid over time and shows that heat transfer fluid temperature remains lower in tank A. Also, in the circle area of the graph, it can be seen that neither heat storage nor heat dissipation takes place in tank A, but heat dissipation takes place in tank B, and the temperature is dropped. This suggests that the cost of utility was greater in tank A than in tank B, because the amount of dissipated heat by the tank was reduced and the steam cost was increased in tank A. In conclusion, we have developed a scheduling system that considers direct and indirect heat recovery in the batch process. By examining the effectiveness of indirect heat recovery using heat storage system, we found that the heat recovery effect depends on the amount of PCM, and confirmed that there is an optimal amount of PCM for cost reduction, depending on the schedule obtained. Future work may include validation in other processes and addressing scheduling issues under uncertainty. Thank you for your attention.
Thank you, Koya. So is there any question for Koya Nakashima? Is there any question? So,
So very nice talk. I have one doubt related to that. What is the delta T you consider for the heat recovery?
Sorry,
What is the delta T minimum you consider for your heat recovery?
so I didn't catch all of that. Could you repeat your question more slowly, please?
So what is the delta T minimum you consider for your study, I'm saying?
did you get the question, Koya?
Yes. Your question is temperature difference. Is this right?
Temperature difference is used for heat recovery.
All right. The temperature difference is 10 Celsius.
So I have one question for you. So you have used GA for this scheduling, isn't it?
Yes.
Typically, the scheduling problem has some combinatorial constants. So how you have handled those combinatorial constants in GA procedure?
Your question is how to determine parameter for GA.
The question
Is that right?
generally the scheduling problems has combinatorial constants. How you have handled in GA procedure?
GA procedure. Sorry. Could you repeat your question, please? I'm sorry.
So see, you have to arrange your units in a sequential manner, isn't it? And there is some logic. So how this type of combinatorial constants are handled in your GA algorithm? All right. So you have used the multi-objective or single objective?
All right. We use evaluation for production volume and utility cost.
So both you have combined, I think you have used a weight to combine them, is it? So that is why I am asking why you have combined it. You could have used them separately and solved the multi-objective.
For your question is how to determine the parameter of W.
So product volume and the utility cost you have combined using weights W and 1 minus W, isn't it? In your equation. Instead of
W
that,
is-
we could have solved them separately in a multi-objective fashion.
mm, hold on, scheduling is production volume and utility cost is depend on scheduling. So production volume and utility cost should consider the simultaneous.
No problem. All right. I think you have solved the single object. I got the answer. Thank you. So is there any question for Koya?